Hi, welcome back. Today we're going to talk about fuels and fueling aircraft. First thing you need to know about burning fuel inside of an engine is you need a lot of air to go with the fuel. It's really the oxygen that we're after, and since oxygen only makes up about 21% of the air, we need a lot of air in order to go with the fuel that we're trying to burn. The ideal amount of air for the fuel is 15 parts air to 1 part fuel. And that is by weight. And obviously air is a lot lighter than fuel, and so you need a lot more air than you need fuel. That ratio of 15 to 1 is what we call the stoichiometric ratio. And if you have thoroughly atomized fuel and burn it at 15 to 1, then every single fuel molecule gets burned and every single oxygen molecule gets burned. In other words, it's totally efficient. Um, that's not where we get our best power, though. Our best power is a little bit richer than that. Not all the fuel is being burned. Um, uh, and that ratio is 12 to 1, 12 parts air to 1 part fuel. So a little bit less air going with the fuel. And that unburned fuel can carry away a little bit of the heat for us. The leanest we can burn the fuel in the engine is about 18 to 1. The very richest that we can burn it is 8 to 1. If you try and burn it any leaner than 18 to 1 or any richer than 8 to 1, then the flame gets too cold and goes out and the engine quits. So how much air is that? You really don't need to know this as a pilot, but just out of general interest, 1 gallon of AvGas weighs 6 pounds. A cubic foot of air weighs 0.07651 pounds, which obviously is very, very light. So if we want to burn it at best power, 12 to 1, then we have to consume almost 1,000 cubic feet of air with each gallon of fuel that we burn. So for a Cessna 152, for instance, that's 6,000 cubic feet per hour, or about 100 cubic feet for every minute that we're running the engine. Now, we don't know how much air is coming in. There's no real handy way to measure that for us. But we can get an idea of what the mixture is doing by measuring the temperature of the exhaust gases as they come out of the engine. And we do that with an exhaust gas temperature gauge, EGT. There's a probe that, just like you would guess, goes into the exhaust pipe and measures the temperature of the gases coming out. They're typically read out in hundreds of degrees Fahrenheit, and each of the little divisions is 25 degrees. Here I've got a chart that shows the relationship between exhaust gas temperature and mixture, where mixture is lean towards the right side of the graph here and rich towards the left side of the graph. And I made a little cartoon EGT gauge so I can show you how to use one. So here's about where full rich is going to be. So we've gotten up there, we've leveled off in our cruise, and we want to lean the mixture out for cruise. We would only do this, by the way, for airplanes. For helicopters, we don't touch the mixture control. It's just too dangerous. We'll talk about that a little bit in class. So we're up there to cruise. We want to start leaning it out, and as we do, we see that the exhaust gas temperature comes up. And we continue to lean until the exhaust gas temperature drops a little bit again. And then we go back to where it was highest. And then there's a little knob that we can turn to set the skinny needle right there at where the peak EGT is. And that's what the little set needle is for. That's a placeholder so we know where peak is. And then we can adjust the mixture either to the rich or to the lean side, and either way we go, the temperature is going to drop. What you'll find if you read your pilot operating handbook carefully is that the manufacturer recommends that you go 25 degrees or more on the lean side of peak. Most operators, however, have found that they get more life out of their engines if they go to the rich side of peak. Whichever it is, we adjust the mixture further, either rich or lean, until we get a 25-degree drop from rich. Some companies even go 50 degrees uh, rich of peak. But either way you go, you're looking for the difference between peak and where your EGT is. Specific fuel consumption is a way of measuring the efficiency of the engine, and it is represented in the number of pounds that you have to burn in order to get each horsepower that you produce per hour. For our engine in the 152, you're looking at about a half a pound per hour for each horsepower that you produce. So it really doesn't vary much from one power setting to another, the specific fuel consumption. But since you are burning maybe more or producing more horsepower at a higher power setting, then you multiply that zero point 0.5 times a bigger number of horsepower and you get a bigger fuel consumption. Most aviation reciprocating engines are right about a half a pound per hour per horsepower. I believe that you would find that that is the case for all of the engines that we're using, within a tenth of a pound per hour in most cases. The only ones that are more efficient than that are diesels and and if you water cool an engine so that you can run it harder, that gives you a little bit more efficiency. You can get the efficiency to about 0.4 pounds per hour per horsepower that way. AvGas has a number of requirements. The first and most important is that it is approved, and it has to be approved either in the pilot operating handbook, which means it's listed in the type certificate and data sheets as being approved for the aircraft, or you have to have a supplemental type certificate that allows you to run a different type of fuel. For instance, a lot of general aviation aircraft have a supplemental type certificate that allow them to run unleaded automotive fuel. But you have to have it approved. That's all the FAA cares about, because their view of this is the only way it can get approved is if it's tested thoroughly. And so really that's all that matters. You could have the best racing fuel ever designed, but it can't go in the airplane or the helicopter unless it is approved by the FAA. It also has to have a low freezing point. We don't want to get up there to altitude where it's really cold and have it freeze up in our tanks. It also needs a high boiling point because the pressure is very low at higher altitudes, and that lowers the boiling point, and so the fuel could burst into a boil in the lines that are going up into the engine compartment. We call that vapor lock. And so we need something that is resistant to that. It also has to have good vaporization. That means that we can break it up into its tiny little pieces so that it can be efficiently burned easily. It has to have good anti-knock characteristics. That means resistance to detonation or anti-pinging characteristics. It needs to be clean. You'll find that AvGas is considerably cleaner than AutoGas. And it has to have good handling properties. We want to be able to take a hose and get up on a ladder and pump it into our airplane or helicopter. We don't want to have to put on a hazmat suit to do that, or have it cooled with liquid nitrogen or something like that. We need something we can pour into a bucket and then pour into the airplane, something really easy. Now, alternative fuels, again, still have to be approved. So again, you need a supplemental type certificate for that. On the issue of automotive gasoline, I have had some bad experiences, which I'll talk about in class with you. You need to be aware that the supplemental type certificates require certain standards that have to be met, and not all autogas meets that standards. Oregon has no regulations that govern the quality of the automotive fuel here. And so if you're going to use it, you have to be very careful where it came from and get the fuel jobber to verify that it conforms to the supplemental type certificates standards. It's an ATSM that they have to conform to. There are some light sport engines that are designed for unleaded automotive fuel, and so if it's listed in the Pilot Operating Handbook as being approved, then you can do it. A word about vapor pressure. This is an important and often overlooked characteristic of the fuel, and it's measured in something we call Reid vapor pressure, which indicates the amount of atmospheric pressure needed in order to hold the fuel in a liquid state. And so if the vapor pressure is too low, what that means is you have to have very low pressure in order to vaporize it, and then it won't vaporize properly, and you'll end up with big clumps of fuel going up into the engine, and that doesn't burn very well. If the RVP is too high, then it bursts into vapor too easily, and then you could have it do that in a fuel line as it goes into the engine compartment, and then you get vapor lock. That bubble of vaporized fuel blocks any more fuel from going to the engine, and you starve your fuel for your engine. Octane is a measure of the resistance to detonation for the fuel. So how much temperature and pressure can we put it under without it detonating? If you don't have a detonation problem, then the higher octane fuel really doesn't do anything for you. So if you've got a car and it runs fine on regular, there's really nothing to be gained by putting premium in it. On the other hand, if you have a car and you hear it knock from time to time, you're getting some pinging, then a higher octane fuel will oftentimes solve that problem. The way we get high octane in aviation gasoline is with lead additives. In particular, it's tetraethyl lead is the chemical we use. It's a liquid additive that gets put into the fuel, and it yields a higher anti-knock rating, a higher octane rating. It also fouls spark plugs and shorts them out, making the engine not run smooth, leaves deposits in the cylinder that can cause pre-detonation, and it also poisons the air. There's really nothing good about it except that it gives us a higher octane rating. Unleaded AvGas is supposed to be coming here, and in fact it's supposed to be here already. It was due last year. However, there were some issues, in quotes. We don't know what those issues are, but the FAA did a bunch of testing on the unleaded AvGas replacements, and there were some issues that needed to be ironed out with them. It'll be interesting to see how long that takes. We dye the fuel, gasoline in aviation, AvGas. And we dye the 100 low lead a blue, as seen here. There are other colors, which I'll go over here in just a second. The interesting thing is that they've chemically designed these dyes to cancel out. So if you mix some blue and some red, you don't get purple. They turn each other clear, which is a really interesting and handy thing. But it's important to know what those colors are. Now, AvGas has historically come in about 4 flavors: 80, 100 low lead, 100, and 115. Just out of historical interest, they actually used to be called with 2 numbers. So 80 used to be 80, 87. There used to be 100, which used to be 100, 100, 130. And then the 115 used to be 115, 145. And the 2 numbers referred to the anti-knock characteristics at a lean setting versus a rich setting. Well, the fuel manufacturers and the FBOs got tired of having all these different kinds of fuels, and so they came up with a fuel that would work in both aircraft that were designed for 80 and aircraft that were designed for 100. And they call that 100 low lead. Now, the lead is where we get our octane, and so you can see by these numbers here, the 80 only has a half a milliliter per gallon in it. The 100 low lead actually has 4 times that. So the low in low lead is only relative to the green fuel, which is the 100, which has yet even more lead in it. It's 4 milliliters per gallon. My 150 is designed for 80, But of course that's not available now, so I use 100 low lead in it, and it runs fine on that. But since it has 4 times the amount of lead that I need, I have to be careful to take the spark plugs out and clean them off from time to time in order to make sure that they don't get fouled up with lead. I have run 100 in 152s. Once again, you have to be very careful to lean at all times and clean the spark plugs often. The purple fuel you're not going to run into. That's really for very high performance aviation engines, like you'll find it at the Reno air races, for instance, or something like that. But you won't typically find it at an FBO. And in fact, there's only one of these that you're going to find in an FBO as a general rule. Once in a while you'll find 80 out there, but for the most part the red, the green, and the purple are gone. And all you have to worry about is the blue. If you do run into some red, just know that you can't use that in your 152 or your 172 or your R22. You need a little bit better octane than that. Fuel contamination. There are a number of types of fuel contamination. We're going to go through those real quick here. The most obvious is solids, which they can build up in the tank over years, but they can also be introduced during fueling operations. And so we're gonna talk about that quite a bit in class, and we're gonna probably go out and take a look at the pumps and maybe even pump a little fuel into an airplane or something, because the caution you use during the fueling process is very important. Any solids that do get into the fuel system have to be removed by whatever filters you have in place in the aircraft. Surfactants are what they call partially soluble things that get gooey when they're in the fuel tank. Best example of this would be the sealant they use to seal up certain fuel tanks. When it's exposed to something like alcohol, sometimes they will partially dissolve. Water is a contaminant. It is fortunately heavy and so tends to precipitate out into the bottom of the tank. Um, and that's where we sample it, and we keep sampling until we don't have any more water. A couple of little tricks that it can play on you here. First of all, if it's AvGas, it does drop out of AvGas fairly quickly. Um, if it's Jet A and it's cold, the water can be held in suspension for a long time and then slowly precipitate out. So you have to be a little bit careful of that. If the AvGas has alcohol in it, so if you take on a load of automotive fuel that inadvertently you've got some auto fuel that has alcohol in it, the alcohol can hold water in suspension and then precipitate the water out over time. So you have to be, that's another reason to be very careful of auto gas. But in general, it's fairly easy to get out. Oh, one other trick that it can do is it can freeze. If you get a bunch of water in there and then it gets really cold at night, it can stay frozen, and so it doesn't come out when you sample it. And then during the flight, if it warms up, now you've got water in your fuel and you could have a problem. Soluble fuel contaminants is another possibility and probably one of the most common. And the most common soluble fuel contamination is the wrong kind of fuel. You, for instance, put Jet A into a tank that's really only supposed to hold AvGas, and that will make the engine fail. So you have to be super careful about that. Microorganisms, there are essentially algae organisms suspended in the fuel, and if the fuel sits in a fuel tank and water gets into the fuel tank with it, they will jump into life. They'll start multiplying, and the nasty thing about them is it breaks the surface temperature of the water and makes it stick to the inside of the tanks and to make it harder to come out. It's pink, and so if you get a sample of fuel with a little water at the bottom and the water is pink, that's microorganisms that grow in the fuel. So you have to be extra careful with that happen to make sure you slosh the tank and try and get all the water out. Some things to keep in mind when fueling. First thing is guard against contamination. Remove water from around the filler neck, if the filler, especially if the filler neck is recessed in the wing. Shield the filler neck from rain if it's raining really hard. Um, Never leave the cap off and walk away because contamination can get in there with you uh, while your back is turned. Also, you may forget about the cap. So even if I'm stepping down off the ladder for just a second to reset the pump or something like that, I put the cap back on and then I just take it off again when I get up there. Take a quick look at the pump filtration system. If you're at a remote location, you're stopping at an FBO that you've never been at before, take a quick look and make sure that it's well maintained, that it doesn't look like the filters haven't been changed in 30 years. Take a look inside the filler nozzle. So before you start pumping, just look down the filler nozzle and make sure that it's not filled with dirt. Consider non-cross-feed fuel selector position. So, um, and this has nothing to do with contamination, by the way, but what this does have to do is getting the most out of your fill. So if you have something like a 172 and you have the fuel selector in the both position, then the fuel can cross feed. So you fuel up one side, and while you're getting down off the ladder, moving the ladder over and getting up on the other side, some of the fuel now has run into the second tank. And now you fill that tank up and the fuel runs back, and so you've shorted yourself a couple of gallons, and that could be the couple of gallons that was going to get you to your destination. Guard against the wrong kind of fuel. Be really kind of paranoid about this, and don't let other people put your fuel in there unless it looks like they're a professional. Take a look at what the pump says that you're getting fuel out of. If the pump isn't labeled in any way, be highly skeptical. I have been sold AvGas before that the FBO claimed was 8087, turned out to be AvGas. So really watch for it. Guard against static. So there's a ground wire that you have to connect, and we'll show you how to do that in class. But you pull it out off of a spool and clip it typically to the exhaust pipe or a bare metal nut or bolt someplace that's handy. What that does is it keeps sparks from happening right at the fuel nozzle there while you're trying to fuel the aircraft. Also, while the fuel is flowing in there, it can actually create static electricity as it flows through the hose. So I keep the nozzle against the side of the filler neck. That way there can't be a spark. Guard against damaging the aircraft. We pay a lot of money to paint these things, and so be careful and respectful of the paint job. Don't leave the nozzle hanging in the hole. There are a lot of aircraft where the fuel filler neck is not structural enough to handle that, and you can crack it or bend the sheet metal around the hole. Don't drag the hose over the wing. I usually toss the hose up over my shoulder so that it won't touch the wing. Be really careful with the ladder that it doesn't blow into the aircraft. And be also very careful where you step, that you don't step on something that's fragile. Also be careful where you step in regards to injury. It's really easy to end up falling down when you're fueling an aircraft, and we'll talk again more about that in class. But be prepared to have somebody give you a hand with things if you need to, and take your time. Don't be in a rush when you're doing this. If you're at a remote location and you don't have fuel pumps, you're filling out of cans, Jeep cans. Make sure that the fuel cans that you're using are dedicated to AvGas. AvGas can be filtered as you put it in. Something that they don't put in the books anymore, but it used to be something you actually had to know to be a pilot. A chamois, a real one, not an imitation one, but an actual chamois skin, works really well as a if you're using a funnel to go into the airplane out of a can. You can put the chamois in there. The fuel will pass through it fairly quickly, but it's a very fine filter, so dirt will get filtered out, but also it has the characteristic of picking up water. So as water droplets go through, the chamois will grab the water but let the fuel pass. That's it. We'll go over some pointers on actually putting fuel into airplanes when we get into the classroom.